So, welcome you all to this fourth problem solving session. We'll wait for another 2 3 minutes for the audience to join and then we can begin. I hope I'm audible. Okay, let us start the session. So, today, if you remember, last time we discussed amplitude modulation related model questions and we briefly get into the, of course, um, the pros and cons of amplitude modulation. We see that power efficiency at best case scenario is only 33.33% for ordinary amplitude modulation. That's where we move into DSBSC or double side band carrier suppressed uh, uh, sorry double sideband suppressed carrier modulation scheme, where basically we refrain from transmitting the carrier so that the efficiency increases because we are not spending energy on transmitting the carrier now. But it turns out today we are going to discuss DSBSC in more details, and we'll also show that even DSBSC has its own pros and cons, and we'll discuss two seemingly better options we have, that is quadrature amplitude multiplexing or QAM, and another is SSB or single sideband modulation. So now let us move to our first question of today's session. So if you remember, last time we discussed that one of the major issues with DSBSC modulation is that, as the name suggests here, is here SC suggests for suppressed carrier here. And we also discuss if there is no carrier, the major problem that arises is the synchronization issues. Synchronization issues at transmitter and receiver. So what do I basically mean by that? This carrier we are talking about, this needs to be generated at both transmitter and receiver end, and there is no guarantee that the carrier being generated at the transmitter can you please mute yourself? It is the background noise is yeah, as so I was discussing, the local oscillator at both transmitter and receiver are responsible for generating the carrier. So let me write it down. So let us, for assumption, consider our carrier is cos, let's say 2 pi fct, that the local oscillator is supposed to generate a transmitter and receiver n. So turns out in ideal scenario, what we expect, that both the transmitter side and receiver side oscillator generate cos 2 pi fct itself, cos 2 pi fct itself, but that is the ideal scenario. In practice, what happens, if transmitter generate cos 2 pi fct, receiver generate cos 2 pi fct plus phi, some phase offset here. So this is what we called lack of synchronization, lack of synchronization. And we have seen in last session that such a phase offset is going to distort your message signal that you transmitted. So basically at receiver end, while you are demodulating your message, instead of getting empty, you will be getting empty cos phi, so that you can uh, visualize as somewhat of a rotated and distorted version of your message signal. For example, if I pick this message signal from QPSK constellation, let's say, where I pick one of those 4 symbols, let's consider you transmit this, but now since there is this lack of synchronization, a phase offset is introduced. So instead of empty, you get empty cos phi. So in constellation diagram, it is equivalent to this message being shifted to this, maybe something here. So that is of course not a part of standard QPSC constellation, so you will have a hard time to find what is being transmitted. That is why I am saying this is the distorted message. So I guess we can agree on this matter, that the phase synchronization, let me write down the conclusion here, phase synchronization is going to cause erroneous demodulation. So you need to fix that, of course, since it's a DSBSC, so we cannot really go back to our ordinary aim where we can basically transmitting the carrier, spending a huge power behind that, which is essentially transmitting no information. So what we can do in absence of carrier, it turns out at the receiver end you just need a simple circuit. So instead of getting into the math first, let me draw the circuit and how it behaves. So that would help you better to visualize how this phase synchronization matter can be handled at the receiver end. So let's assume this is your DSBSC signal coming in. We have seen the standard notation, that is AC, empty, and let's say carrier is cos 2 pi fct. Fine. Now as of now I was talking about this local oscillator, so let's uh, use a slightly advanced version of that, something called VCO. VCO stands for voltage controlled oscillator. So its job remain the same, that is generating the carrier, but it is slightly advanced in the context how it operates. We'll come to that in a minute. So essentially VCO generates this carrier, right? But importantly, it generates carrier with a phase offset now, 2 pi fct plus phi. I mean, that is something inherent, so it cannot help it really. Another, what I do, whatever VCO output is, that is cos 2 pi fct plus pi, that locally generated carrier, I shift the phase of that by minus pi by 2 and do the similar processing at the top branch. So VCO originally generates this. Now I am asking VCO, I am just passing this output of VCO through this phase shifter. So essentially I am just getting here sine 2 pi fct plus phi, multiplying it, passing. Now both end I plan to pass it through the low pass filter. That the goal here is to essentially recover the baseband signal. So let me write it down here. Recover the baseband part. So let us just see what we are going to get in this LPF. Let us, our signal is AC MT cos 2 pi fct, and I am multiplying it with cos 2 pi fct plus phi. If you do the math, you will see you are going to get this. From this multiplication, this comes out to be the baseband part. Another part will be there that corresponds to higher frequency 2fc, but since we are passing it through low pass filter, this part is what is be left. So let me write it down here. AC MT cos phi by 2, that is what I am getting here. Similarly here, if I do the math, I will get AC MT sin phi over 2, because here we are multiplying with sine here. Now the engineer's technique, the receiver, the engineer's device, so they say that let us, why not use a phase discriminator here. So this one here they are calling PD, or phase discriminator. Now the name sounds quite heavy, but what it basically does, it multiplies the signal, both this signal. So what we are getting here, AC square m square t cos phi sin phi over 4. That is basically what this phase discriminator is generating. Now basically what we are going to do, we are going to feed this to this local oscillator. Remember the name we talked about first, it's voltage controlled oscillator. So basically its job remains same, generating the carrier free signal, but there is a part of it which says that it's voltage control. So this voltage, this AC square m square t cos phi sin phi over 4, that is the output of the phase discriminator, is going to control what the VCO going to generate. Of course the frequency doesn't change. When I say voltage control, this voltage control applies to this phi. Now let us see how it works. So remember the input to VCO is this AC square m square t cos phi sin phi over 4. Now let me consider one scenario, case 1, where the phase offset is positive. That basically means the carrier generated at receiver end is leading the same or the counterpart in its transmitter. So what is going to happen then? If I carefully look at this, for phi positive, your cos phi and sin phi both are going to be positive. Anyway, this part is AC square m square t, so of course that's going to be positive only. So now the voltage that control the oscillator this one is also positive. There is another scenario possible when phi is negative. That means the carrier generated by the receiver is basically lagging its counterpart in transmitter. So for phi negative, if I see that cos phi still remain positive, because you know cos of minus x is cos of x only. So cos, you can see, kind of absorb the negative part, but sin of phi now is negative. That is the only negative part in the whole entire expression. So we are left with this voltage being negative. So what we get, for leading phase, voltage positive, for lagging phase the voltage is negative. Now remember that voltage control part. Now I am designing my VCO such that the voltage is positive, it is going to decrease the phi, and when voltage is negative, it should increase. Sorry, let me remove the part here. So things may not be apparent for you from this discussion, that how does it still fits in the argument. So let us draw this value of like one dimensional line over which phi can lie. Let's say it runs from minus pi to pi. I am taking this is where phi is basically unique, and now this is the point 0. Now 0 is the point we want to achieve, right? Ideal scenario. What does phi being 0 that means the local oscillator, the carrier signal generated at receiver, is neither lagging nor leading its counterpart in transmitter. That means they are synchronized perfectly. So remember, this is the relation I am enforcing in voltage control oscillator. So that when you have a positive voltage, you decrease the phi, and when a voltage negative, you increase the phi. Now let's assume the positive voltage when happens, phi is greater than 0, right? So it's somewhere here. Phi greater than 0, let's say it's somewhere here. So if my phase offset is here, something positive, what I need to do? I would ideally like to move it towards 0, right? And since this is a positive quantity, moving to 0 is equivalent to saying we have to decrease phi, right? Think just the opposite. We have seen that voltage is negative for lagging phase. So when phi is negative, so phi negative means it should be somewhere here. So when phi is negative, we see the voltage is negative. So what I would like the voltage that is fed to the voltage control oscillator to do, I would of course would like to move the phase towards 0. And what it means by a negative value to move towards 0, it means I have to increase phi, right? That is where I have established this relation, that how I want my voltage that is being given to voltage control oscillator to impact the phase offset. We have seen for leading phase, that is for phi greater than 0, voltage is positive. Since it's a leading phase, I would like to bring it back to 0. So I tune my voltage control oscillator such that the positive voltage lead to a decrease in phase offset, so that it moves towards 0. Similarly, for lagging phase, when phi is negative, it turns out my voltage is negative. So ideally, I would like to move this phase towards 0. So that's why I have to increase it to move it towards 0, since it's a negative quantity. That is why I tune it such that the negative voltage lead to increase in phi, and that is how this circuit operates. It is slightly complicated compared to what we see used for demodulation for ordinary amplitude AM, that is the envelope detector, but it's still remarkably simple. So you can see that that crucial problem that the DSBSC modulation encounters regarding the synchronization can also be solved by this kind of simple circuit. Local oscillator and phase shifter and low pass filter and phase discriminator, these are inexpensive things apart from the local oscillator, but it need to be there anyway. So basically using this few low pass filter and phase discriminator and phase shifter, you can achieve this kind of phase locked loop that would ensure synchronization between the transmitter and receiver, like at very early stage of demodulation. So this is how synchronization is achieved. And this particular circuit what you are seeing is nothing but Costas loop. Now let us move to our next question here. Which is regarding, given the message signal MT and carrier frequency FT, we are given the modulated signal expression AC MT cos 2 pi FCT, and we are supposed to find out whether it's SSB, DSBSC, or vestigial sideband VSB, or quadrature carrier multiplexing. So we know that cos 2 pi FCT corresponds to this expression, right? 1 over 2 e to the power j 2 pi FCT plus e to the power minus j 2 pi FCT. And if I do the Fourier transform of that, what I will get, it basically impulses at fc and minus fc, right? Now since this is a multiplication in time domain and frequency domain, what we are going to see, convolution, right? If mt is frequency, represented Fourier transform is mf, the spectrum is mf, then I am going to convolute mf with this. So essentially what I will be getting, shifted version of m at like this, shifted to the center frequency fc, and of course minus fc here. So this is mf minus fc, this is m f plus fc. So this is what you can see, is there is no carrier present, so suppressed carrier, and you have both the sideband here, so it's a double sideband suppressed carrier or DSBSC modulation. This question part is easy, but I would like to discuss this quadrature carrier multiplexing part. As of now, you have seen ordinary amplitude modulation and DSBSC modulation. But what is this quadrature carrier multiplexing? So this QCM here, QCM basically make use of two carrier signal. In DSBSC you can see here it's still using single carrier signal, single carrier, and same in ordinary amplitude modulation also. But QCM onwards things started changing. How so? I am using two carrier signal, and the important part is that I am going to use the same bandwidth actually when I say I am going to use two carrier signal. So basically let us see what are these two carrier signals. So one is cos 2 pi fct, another is sin 2 pi fct, right? So what is so different about them? So if I look at it from the principle of trigonometry, we know that phase difference between these two carriers, phase difference is pi by 2, right? Pi by 2 phase difference between these two carriers. So when I say two carrier signal, it's of course implied that I am not going to use them for transmitting the same message signal, right? So what is the standard expression of quadrature carrier multiplexed signal? Turns out it is given as like this. So this cos 2 pi fct and sin 2 pi fct are two carrier signals, and mq and mi are two message signals, right? So this one here, cos 2 pi fct, we call it in phase carrier, and this carrier here sin 2 pi fct, this is named as quadrature carrier. So that is another reason of saying that the the carriers are said to be quadrature. What I mean by that, I will come to that in minute. So these are the two messages, of course, MIT and MQT. So MIT is the message transmitted over in phase carrier, message transmitted over in phase carrier, and MQ here is the message transmitted over quadrature carrier. Now see, now note the difference first compared to DSB-SC or earlier ordinary amplitude modulation or AM. What we have seen, we are as of now transmitting one message signal over one carrier. But now the catch is, now I am using two carrier signal to transmit two messages, but they are over the same bandwidth. So your question would be, of course, how is that possible? Earlier I was not transmitting because there was going to be interference, and how come this doesn't appear here? So turns out this can happen if you can make the two carrier signal orthogonal, and how that is ensured, I'll come to that. So if I multiply this two, cos 2 pi fct and sin 2 pi fct, what I am going to get? This is nothing but sin 4 pi fct, right? And what is this? This has spectrum at 2fc, right? So its baseband content is 0. So if I pass it through a low pass filter, I'll get 0. That is means it doesn't have mutual impact on top of each other. So that is why I am saying these carriers are orthogonal to each other. You can assume, visualize this as they are kind of coexisting, but at the same time, since they have this particular property, their phase shift is pi by 2, and so when you basically multiplying them, so when I say multiply here, that is a symbol of interacting. When they are interacting, you can see that has no baseband component. Its baseband component is 0. When they interact and pass it through a low pass filter, they have no mutual interference. So that's why these two carriers are orthogonal to each other, and we will see that this is the key property that enables this QCM to transmit two message signal at the same bandwidth. That is the key advantage of QCM. So of course the next immediate question comes to mind, that okay, fine, you are using two carrier, you are transmitting MQ and MI. MI is the in phase signal, you can say, and MQ is the quadrature signal. But the equally important question is how to demodulate both MI and MQ, because if this cannot be done, the whole purpose dies basically. So no matter if I transmit 2 or even 4 carriers of 4 signals or 4 carriers, the moment I fails to demodulate them at the same time, it basically doesn't make any sense. So demodulation is equally important. So I need to look for simultaneous demodulation. So let us see how we can do that. Remember what we are transmitting, the standard expression of QCM is AC MI T cos just a minute. cos 2 pi fct minus AC mqt sin 2 pi fct. Let us multiply it with cos 2 pi fct and see what we are getting here. So here I will have AC MIT cos square 2 pi fct minus AC mqt sin 2 pi fct cos 2 pi fct. This I can write as 1 plus cos 4 pi fct over 2, and this is nothing but sin 4 pi fct over 2. This comes down as follows. So if I try to find the baseband component, because that is what I am interested at the receiver end, what I am getting? AC MIT over 2, right? This is my baseband component. What about the others? AC MIT cos 4 pi fct over 2 minus AC mqt sin 4 pi fct over 2. So these two here, these two terms have their spectrum centered around 2fc, right? So essentially if I pass this whole thing if I pass through a low pass filter, essentially successfully recover MIT. So that is about the in phase signal. What about the quadrature part? So let us just look into that. So to recover MQT, what you need to do? Let us write down the standard QCM signal. So here I am getting AC MI cos 2 pi fct sin 2 pi fct. So let me write it down at a time. Sin 4 pi fct by 2 minus AC MQT, write down T here, sin square 2 pi fct, and that is nothing but 1 minus cos 4 pi fct over 2. So you have seen that if I pass this through low pass filter again, only baseband component that is going to survive is this, because other two as earlier are centered around 2fc. So we have successful recovery of quadrature signaling component also. So what is the key message here? So earlier, if I compare with ordinary M and DSBSC, we are transmitting uh, a single message over a single carrier which is occupying a particular bandwidth. For QCM, what we are seeing, we are using two carrier signal, but remember they are not occupying twice the bandwidth, they are occupying the same bandwidth. But now using this two carrier signal, I can transmit two messages. And why I can transmit two messages? Because these carriers are quadrature, or another way of saying is orthogonal in baseband. So essentially I can kind of, you can say, enable parallel transmission of two message. So let me write it down here. QCM enables parallel QCM enables parallel transmission of two messages as over same bandwidth as both in phase and quadrature carriers share same bandwidth. So I guess you are able to point out the benefit of it now. Earlier, if for a fixed bandwidth you were using a single carrier to transmit a single message, but QCM gives the opportunity that okay, you use the same bandwidth, but you can have this particular in phase and quadrature carriers which are orthogonal to each other, therefore they don't interact in the baseband domain. So essentially what you can do, you can transmit one message over each of them, but since they are not interfering at the receiver side, you can demodulate them separately, but crucially that bandwidth uses remains same. So earlier you were able to send a single message, now we can send two messages at a time because of this orthogonality property of the underlying carriers. That is the key benefit of this QCM, or quadrature carrier multiplexing. Okay, let us come to a very crucial transform that you are going to see again and again in the course. So that is the Hilbert transform, and we are supposed to find the frequency response of Hilbert transform. So let us see why we are so concerned about Hilbert transform, or what it does actually and how it is useful, though that we will see going forward in the course. But let us see what we mean by that Hilbert transform. So let's say I have a signal MT, I am passing it through a Hilbert transformer. This is my Hilbert transformer, and I denote its impulse response in time domain as capital small h capital HT of t, and the output you are getting, let's say m hat t. Okay, so by the property of convolution in time domain, what you are getting, your signal after passing through Hilbert transformer m hat t is given as convolution of mt with impulse response of Hilbert transformer. Now let me give the answer immediately, but the discussion doesn't quite end here. So this impulse response, if I take the frequency considered spectrum or Fourier transform, we denote it as capital H, HTF, and is given as a very unique expression minus j sin f. So that can actually takes three values based on the different regimes. First of all, consider positive frequency range. What value it can take? Okay, let us instead of talking about the whole part, let us talk about the only sign of f part. For f positive, it takes value 1, right? For f negative, it takes value -1, and for f0, it takes value 0. Okay, so if I try to visualize this, let my x-axis be frequency axis and y-axis be sin of f. So what I am going to see here is this, right? For positive frequency takes constant value 1, for negative f takes value -1, and at 0 there is a shift. Now let us consider the same thing, sin of t in time domain. That doesn't really change anything apart from the naming of the x-axis, so that remains same. 1 here and -1 here. And let's say I am now interested in the derivative of this function here. So when I talk about the derivative in analytics, in visually we can interpret at what rate it's changing, right? So let us just try to see what the graph should be depending on the classical definition of derivative, which say that it is nothing but the rate at which the signal is changing. Tell me, for a positive, slightly positive f, let's say slightly more than 0 onwards, what is the rate of change? It is going to be 0 only, right? Because it's going to be the constant across the whole regime. Across the entire positive frequency range, it takes a constant value. That means for f tends to 0 plus, slightly more than 0, it's going to take value 0 only, like that. What about negative domain? Again, it takes a constant value for f minus, so f 0 minus, again constant value, so rate of change is 0. At 0 something interesting happen. You see at 0 minus it has a value of -1, and at 0 plus it has a value of 1. So you can see a shift of 2, and that happens immediately. So that derivative actually is not smooth. If I say it like this follows, let's see whether you agree with this or not. I am calling that this derivative at t equal to 0 is given by 2 times delta t. Delta function we have already talked about in previous sessions. Now it's 2 delta t. So it's like this. Remember, delta t has a infinite height, right? And that corroborates with the claim here. Here you can see that change is not happening. This -1 to 1 is not happening over a finite width. It is happening instantly. So that gradient is therefore the delta function, which has a infinite height and 0 width, and the value is of course 2 because the shift in value is 2. So essentially this is what it's going to be. It turns out I can this one here applies d dt sin t. I can claim it as 2 delta t, because for other regime it also holds, because for any value that is t not equal to 0, it's 0 essentially. So this is what its expression is going to be. So let me introduce a slide here to reinforce the points. d dt of sin t is 2 del t for t 0 and 0 otherwise. And let me also write down the Fourier transform of del t. It's nothing but 1. Now let us move for any standard function xt. Fourier transform is given by xf, and if I consider d dt of xt, its Fourier transform is given by j 2 pi f xf. Now let us replace xt with sin t. So d dt of sin t is j 2 pi f xf is nothing but Fourier transform of sin t, right? So just now what we have seen, that d dt of sin t is 2 delta t, and delta t has a Fourier transform of 1. So if I take Fourier transform of this, I will get 2, and that is same as this here. So let me just equate j 2 pi f Fourier transform of sin t is 2. That is equivalent to saying Fourier transform of sin t is 1 over j pi f. Now I am going to use the time frequency duality. Which basically say if small xt has Fourier transform capital Xf, then capital Xt will have Fourier transform small x of minus f. Let us apply here. Let me write it down side by side. Sin t has Fourier transform 1 by j pi f, then sine of minus f as Fourier transform 1 over j pi t. And what is sine of minus f? It's nothing but minus of sine f as a Fourier transform 1 over j pi t. Now remember Hilbert transform, what we have seen. The Fourier transform of Hilbert transform is given as minus j sine f. So I can get the time domain impulse response of Hilbert transformer as inverse Fourier transform of JHT. Sorry, if I multiply here j, I will get 1 over pi t, right? So that is 1 over j pi t into j, that is 1 over pi t. So this is the equivalent time domain response of Hilbert transform. So let me write it down here. Equivalent time domain impulse response of Hilbert transformer. So the frequency response, as we have seen, is this. Let us consider the power of this DSBSC signal here. We have 2 cos 4 pi t cos 5000 pi t. If we put or match that with the standard DSBSC expression, that is AC mt cos 2 pi fct, then we can see AC is 2, mt is this, and this is this. So the when we are supposed to compute the power, it is given as expected value of AC square m square t cos square 2 pi fct. Now they can be all separated. AC square is a constant, it comes out. Here we have expected value of m square t and expected value of cos square 2 pi fct. This here we have multiple times seen, its power is 1 over 2. Similarly, this one here is nothing but expected value of another sinusoid. Nothing really changes, it's still 1 over 2, and AC square is 2 square, that is 4. So we have 4 times 1 over 2 times 1 over 2, that is 1. Now comes another important topic of today's session. We have already seen ordinary AM, we have seen DSBSC, we have seen quadrature carrier multiplexing. Now we are going to see the SSB or single sideband modulated signal. So let us first try to see that why SSB comes into picture in the first place. We are happy with DSBSC, so what is the issue there that motivates the engineers to come up with this concept of SSB modulated signal. So let us start with DSBSC here. DSBSC, where we have MT times cos 2 pi FCT. I am just ignoring the amplitude part AC because that's constant, so you can safely ignore that. And let us consider this Fourier transform to be MF, which, if I plan to draw the spectra here, looks something like this. This is FM, this is minus FM. So if we talk about one-sided bandwidth, it's FM. Now basically we are multiplying with cos 2 pi FCT. We have seen that multiply with cos 2 pi FCT in time domain, complex sinusoid, basically translate into shifting in frequency domain. And what kind of shift? This multiplication with cos 2 pi FCT results into this here. You have now basically this, the base shifted to FC. This is FC minus FM, this is FC plus FM. I am not repeating in this side here. So you can see one crucial thing is that in baseband, if we talk about only positive part of the bandwidth, your bandwidth was FM, right? But this is baseband signal because it's centered around 0, and when you multiply with carrier, essentially you are generating passband signal. So this is your passband signal. You can see passband signal, your bandwidth becomes, for passband signal, what is your bandwidth now? It's FC plus FM minus FC minus FM. That is essentially 2 FM. Now see, whatever whatever bandwidth you have in your baseband FM, now when you convert it to passband, essentially you need twice the bandwidth. So passband signal needs twice the bandwidth. And this is where the problem with double sideband suppressed carrier begins, because you can see sorry you can in wireless communication you can see bandwidth as a form of currency or resources, which is basically limited. So you always try to spend minimum resource to achieve maximum gain, right? But when you are using DSBSC, your bandwidth requirement become 2 times. So what I mean by that, so this part here, these two corresponds to lower sideband. Why so? Because its values are lower than the carrier frequency FC. It lies between FC and FC minus FM. So these two here corresponds to lower sideband or LSB, and these two here are upper side bands or USB. Turns out the information content here and here are just replicas of each other, right? For example, if you see here, whatever information content is here, it's just same as that is here. So essentially, when you are using double sideband suppressed carrier, you are transmitting both. So you require a full bandwidth 2 FM, but your unique information lies in a bandwidth of FM only, because the another part is just a replica. So let me write it down here. The information content in lower sideband and upper sideband are identical. So this renders double sideband suppressed carrier modulation redundant. Why so? Because you can clearly see I need not transmit both LSB and USB, which has been done in double sideband suppressed carrier. I can transmit the lower sideband either uh, or the upper sideband. That is what my amount of unique information is. So basically I require half the bandwidth, and so that is kind of the optimal transmission. Double sideband is not as good as it was, as it sound to me. So let me just clarify this point in next slide again. Okay, I mentioned noise is coming. So as of now in my background there is, so what kind of noise you are facing from my end? Like, is it because my surrounding there is not much as noise as of now. So okay, okay, someone speaking here. Sometimes since I'm in my hostel, so people are going outside my room and you will occasionally hear that sound. So that I cannot do much about. But like, is that you are facing on a regular basis? Like, is that pretty much regular, or that is like in between, like infrequent? If that is okay, okay, thank you. I just pray that no one walks outside my door while talking loudly. So as we have seen now, so double sideband is really not required. So let me just reinforce my point here again. So I have two options. What are my options? Basically, I can either transmit this, this is FC, this is FC plus FM, this is minus FC, this is minus FC minus FM, and this is upper sideband. So this is my one option. Instead of double sideband, I can transmit this, or I can transmit this. FC, FC minus FM, minus FC minus FC plus FM. this is lower side band. So either I can transmit this or I can transmit this. See, now unlike double sideband, there is no redundant information. I am only transmitting the half, any one of the half which contains the unique information. So in both this scenario, both these bandwidth, or to be specific, passband bandwidth required is FM, unlike 2 FM in DSB SC. Now in communication, we use a metric called spectral efficiency. We won't get into much details about that as of now, but let me just give the, it's just it's a metric that is used to quantify that how efficiently you are able to transmit the information. So how efficiently, by that how I mean that, since I talked about bandwidth being currency, it's like in a restricted or limited bandwidth, how much amount of data you can reliably transmit. So that is what spectral efficiency as a metric quantifies. So if I try to write a very simple expression for spectral efficiency, it would be something like that, that information sent and what is the bandwidth required for that. So let's focus on the information sent part. This is same for both DSB-SC or lower sideband or upper sideband. These two together we call it SSB or single sideband. See, the information sent remains same for both the single sideband scenario or double sideband scenario. The key improvement comes in terms of bandwidth that is you are spending. So for DSB-SC it's 2 FM, and for SSB it's FM. So you can see information content remains same, bandwidth requirement is half, so spectral efficiency doubled. So that means SSB ensures two x spectral efficiency that of DSB SC. Now the question is, now this looks all nice and clean in math, that okay, I will not transmit DSB-SC because it's sending too much redundant information. What I will do either upper sideband or lower sideband, both of which falls under the scope of single sideband. I will save half the bandwidth and the spectral efficiency will be doubled. So that looks nice and pen and paper. But one thing you have to remember, that you have this, you know how to get this. This is the DSB-SC. Now from this I have to get either this one or this one, and that procedure of getting the SSB spectrum for DSB spectrum is not straightforward. So let me write it down. Process of getting SSB spectrum from DSB is not straightforward. So let us check how we can get that. So you can say that, okay, why not? This is, let me just a minute. So this is my DSB-SC spectrum. So what I will do, if I plan to get LSB or lower sideband spectrum, so what I will do, I will use a filter like this. I have to use a filter like this. So that essentially what it's going to do, it's going to pass anything that is in this domain and stopping the rest of the part. So this is my filter for lower sideband. I can use that filter for LSB. And in case I need the upper sideband, what I will do, I'll just use this. It's just the opposite of what the filter used for lower sideband. I'll just use this one. It is going to not pass anything, any frequency lower than FC, and going to pass all frequency over FC. So this is the filter for upper sideband. So if I talk about this LSB filter, you can write it as expression LSB as 1 if absolute frequency less than equal to FC and 0 otherwise. Similarly, filter for USB, I can write it as H USB as 1 if frequency greater than FC and 0 otherwise. So you can see this one here is nothing but a high pass filter, and this one here is nothing but a low pass filter. And this procedure, this procedure of SSB generation is by frequency discrimination or filtering. Discrimination or filtering, the intuitively you can see at higher level they basically represent the same thing. When you say discrimination, what you are going to do, you are not going to treat every frequency as same, you are going to cut off some frequencies while let some of the frequencies go. That is essentially what filtering is. that is being done by both filters for lower sideband or upper sideband. But the issue is, in this method of SSB generation, you are relying on this kind of sharp cutoff behaviors, right, of the filter for both side. Sharp, sharp ideal cutoff frequency behavior. But the issue is, this doesn't happen in practice. In practice, what you will see something like this. Let me draw another one just to clarify this. Now this is your ideal. Let me draw the ideal for low pass filter for lower sideband. This is what you want, this kind of sharp cutoff. But in practice, what you get is something like this. Till this part, everything is fine. From here, like this. Similarly, like this. So this part of upper sideband is also included by practical low pass filter, because you never have this sharp cutoff filter behavior, and these are called vestiges. So essentially, even if pen and paper, the single sideband passband frequency is FM, it turns out in practice, since you don't have such sharp cutoff behavior, you have this additional frequency. So your bandwidth is not exactly FM, it's slightly more than FM. It is quite less than, like far less than 2 FM, but slightly more than FM. That is the practical behavior. So another method of SSB generation you can use, that is called by the transformer we have just seen earlier, by Hilbert transformer. So let us look at that also. SSB generation. I think we have now seen that what are the problems comes when we use frequency discrimination or filtering method of SSB generation, because you don't have a sharp cutoff behavior, so you land into some trouble. It's not exactly SSB. In lower sideband, some part of upper sideband is present, and vice versa. So that increases the the effective passband bandwidth from FM. So now we look at SSB generation using Hilbert transformer and how it is achieved. So Hilbert transformer, let us refresh our memories. So let me write it down. The spectrum of Hilbert transformer, it is given as minus j sine of f, and if I plan to look at the amplitude of that, you can see its amplitude is 1, because you are taking basically the absolute value of this, which is 1 always. And the phase response, if I try to draw the phase graph of HHTF, what I will essentially get is phase of minus j sine f, right? So if f is positive, sine of f is 1, so it's phase of minus j, which is minus pi by 2 for f positive, zero for f 0, and pi by 2 for f negative. So it essentially shift all positive frequency by minus pi by 2, shift all negative frequency by pi by 2. So if I am to draw a visual representation of that, I'll get something like this. Pi by 2 minus pi by 2. So essentially, if my message signal goes through this Hilbert transformer here, HT, and I get m hat of t, so m hat of t is given as mt convolution with ht, and convolution in time domain, you know, in frequency domain it would become multiplication. So we have mf h h t f, that is minus j mf sin f. And I would introduce another term here, that is called analytical signal. You will see that later in details about it in next session. It is just given by, let's say if I call it AT, it is given by MT, the original message signal, plus J times the Hilbert transformed version of that. Okay. So lower sideband, since it corresponds to lesser frequency than carrier frequency Fc here, it is given as real terms of analytical signal shifted by baseband, shifted to baseband. So how I can get it? So you can see, you can write AT expression MT plus J M hat T, which is the Hilbert transform version of original signal, e to the power minus j 2 pi fct. I can write as cos 2 pi fct minus j sin 2 pi fct. Since we are interested into the real part, so the real, let's pick the two real part only, cos 2 pi fct. Second, third terms are imaginary, so you skip them. Last one is the another real term, that is m hat t sin 2 pi fct. So the lower sideband signal expression is given by mt cos 2 pi fct plus Hilbert transform version of original message signal times sin 2 pi fct. So this is lower sideband spectrum. Now what about its frequency transform? This one here, you know, the frequency transform is given by delta f minus fc plus delta f plus fc, right? And this one, you know, it's 1 over 2j delta f minus fc plus delta f plus fc. Sorry, it should be minus here, it is plus and it is minus, sorry, yeah. Now this is multiplication in time domain. So if I take the spectrum of this, convert the whole thing to frequency domain, this will become convolution, right? So let us write that down. Frequency transform of, we are looking at the lower sideband spectrum. So mt become mf, time domain it was multiplication, so frequency domain it will be convolution with delta f plus fc minus delta f minus fc plus m had f, you know what is that, it is, let me write it down again, Hilbert transformed version of original signal. That is what it is. Convolution with 1 over 2j del f plus fc minus del f minus fc. Now remember this term is nothing but minus j mf sin f, right? So what we are going to get from here, from this we get 1 over 2 m f minus fc plus m f plus fc, right? Let us keep as it is. This one become minus mf sin f by 2 del f plus fc minus del f minus fc. So if I take m f minus fc common, I will have 1 from here, and from here I will get, this is, sorry, this one should be f minus and this one should be f plus, sorry about this, f minus f plus. Similarly here f minus just let me correct the error. Yep, it should be f minus here, should be f plus, and here should be minus. Fine. So now we have m minus fc common, we have 1, and from here I will have m minus fc here minus sin f, right? Minus sin f, sorry, sin f minus fc, because it was convolution. So sin f minus fc. And I will have m f plus fc times 1 plus sin f plus fc. So now let us go and check our question here, which is given as what should be the Fourier transform. So now we have seen the Fourier transform is going to be the fourth one. The fourth one is the correct answer. Let me just verify it once. A minus fc 1 minus yes, fourth one is the correct answer. Now we are given the message signal. We have to find the single sideband modulated signal with lower sideband corresponds to this carrier frequency. So since fc 20 kilohertz, your carrier cos 2 pi fct is basically cos 40,000 pi t, right? Now just now we have seen what is the time domain representation of lower sideband signal is going to be. This is mt cos 2 pi fct m hat t sin 2 pi fct, right? Let me write it down. The lower sideband signal is going to be mt cos 2 pi fct plus Hilbert transform version of signal times sine 2 pi fct. Now let us pick our message signal sine 1000 pi t. So if I take the Fourier transform, it is going to be 1 over 2j del f minus 500 minus del f plus 500, and the Hilbert transform version m dash f is going to be minus j sine f times mf, right? So what I am going to get here is minus 1 over 2 sine f del f minus 500 times sine f del f plus 500. So this part is positive, so this value will take 1. So I will have del f minus 500, and this part corresponds to negative. So here, sorry, it should be sine value will take value minus 1. So minus of minus 1 will become plus 1. It will be del f plus 500. So this is the spectrum of Hilbert transform version of message signal. If I do inverse ft of this, what you will get? You will get cos 1000 pi t. So if I put those values here, mt is sine 1000 pi t cos 40,000 pi t plus cos 1000 pi t sine 40,000 pi t. Now this is sine a cos b plus cos a sine b. That means I have to put sine of a minus b, right? That is 1000 minus 40,000 pi t. That is minus sine 39,000 pi t. So minus comes into picture because sine of minus is minus of sine. So first one is the correct answer for me. Yes, I have taken Hilbert transform for mt because you can see that for lower sideband spectrum we have already seen that the expression is given as mt cos 2 pi fct plus m hat t sin 2 pi fct, whereas m hat is the Hilbert transform version of your original message signal that we have already established here. You can see from here this expression. So this is the yours. If your message signal is mt, the corresponding single sideband modulated signal expression is given by this, and this is the SSB generation via Hilbert transform. And since your message signal is sine 100 sine 1000 pi t, your Hilbert transform version of message signal come out to be cos 1000 pi t. That is how I get it. Is it clear to you now? Oh, sure. Thank you. So let us move to our next question here. That is, I have this signal xt ac cos 2 pi fct and k sin 2 pi fmt. Basically, I was passing it through a square law device. So essentially, I am getting this cos 2 pi fct plus k sine 2 pi fmt, and you are passing it through a band pass filter with center frequency fc. So let us just quickly check what we are getting here. ac square cos square 2 pi fct plus 2 ac k cos 2 pi fct sine 2 pi fmt plus k square sine square 2 pi fmt. So if the output is passed through a band pass filter with center frequency fct, what I will get? So this one you can see this is clearly baseband component far away from center frequency fct, so this will not pass. This one here is going to generate a baseband component, another high frequency component around fc 0, one component around 0 and one component around 2 fc, so it is also not going to pass. So the only thing that is going to pass is this one here, 2 ac k cos 2 pi fct sine 2 pi fmt. So this is your DSB-AC signal going to be. What is that? Here, the fourth one. Again, the power of DSB-AC signal. So I am not getting into the detailed calculation. I have done similar thing for another previous question. You can check that. So you can see we have shown that power of this term is 1 over 2, power of this message term is 1 over 2, and of course it would be, this one would be 2 square times 4. Essentially we need to multiply all these 3, so we'll get 1 here. Let us move to the vestigial sideband modulation scheme. So that we have already briefly discussed. When you try to generate single sideband using this frequency discrimination or filtering, you are, if you are doing LSB modulation, you are tend to have some part of USB because of your practical filter characteristics, and the vice versa, that is for USB will have some part of LSB. So you have to design the filter such that, so what is the condition that need to satisfy. So let me just briefly tell what you have. So let's start with the spectrum as baseband. Okay, so this is our baseband spectrum of message signal MF. We have message signal MT that we plan to modulate. MF is baseband spectrum. Then we do carrier modulation. So when we do carrier modulation, what we get? We get the DSB-AC expression, that is in the pass band, MF minus FC plus MF plus FC. That is what you have in your pass band. Of course, for vestigial sideband modulation, you pass it through a filter, as we mentioned in SSB generation, via filtering or frequency discrimination. So what we have now, MF minus FC times HF. Since it's a convolution in time domain and frequency domain, it's just multiplication, so it's easy to handle. MF plus FC H of F. Now you need to demodulate MT. That essentially means bring the signal to baseband to recover. What we plan to recover is the original spectrum MF, right? That is we plan to recover. So how we do that? We basically need to shift it. So M, here we have MF minus FC HF, right? So if I consider this as F dash, so if it need to become MF, so it would become HF plus FC. Similarly for this one, if it needs to become MF, H will become here H F minus Fc. So this is what I mean by bringing the signal back to baseband to recover MF. Now for distortion less demodulation, what do we need? We need this signal equivalent to MF. We want MF, the original spectrum should be same as what we get the baseband equivalent from this filtering, that is MF times H F plus Fc plus H F minus Fc. And what does that mean? This leads to the condition that H F minus Fc plus H F plus Fc should equal to 1. Then only your demodulation will be distortion free. So your fourth one is the correct answer here. So with this I plan to conclude this session. I have discussed the model question I plan to discuss for today. So thank you for attending the session whole time. If you have any question, please let me know. You can ask me or you can type in chat box. You can mail me later also regarding anything about this content. And if there is no question, then we can conclude the session and we will meet again on next Saturday. Okay, thank you. Thank you. Okay, if there is no question, then I will conclude this session. So good night. Let's meet again next Saturday.